Here we go. 6.03 graph exponential functions. The time has come. So here are two pictures. We've seen exponential functions on graphs a little bit, but today we're really going to learn how to actually graph them. Okay, our lesson goals: graph an exponential function given its equation. Okay, so graphing the exponential function, sometimes you're given an equation. Describe the effect a given parameter has on a graph. So there are different transformations that change the way the line looks. That's what we're talking about when we're talking about effects of a parameter. Determine the equation of the horizontal asymptote of an exponential function from its equation. So horizontal asymptote is something that we're going to focus on as well. Determine the range of an exponential function. We talk a lot about domain, but today we're going to talk about range, again, from its equation. And last but not least, determine the y-intercept of an exponential function, again, from its equations. We're looking at lots of equations today. So, what is an exponential function? Well, it's a function where the variable is the exponent, like you see there and there. This is, of course, a decreasing exponential function. In other words, exponential decay. Notice the base is less than 1. Exponential growth, the base is greater than 1. Okay? And think about it. Well, every power you put is going to be actually making this value smaller and smaller. You'll see what we mean as we go along. So here we go. Notice the bigger the base, B, right here, okay, aka here, here, and here for these three different lines. The bigger the base, the steeper the line. Can you see why? Take a look at it. The bigger the base, the steeper the line. Why? Well, you're raising 10 to the first power, then the second. 10 to the second is 100. This is going to go up to 100 by the time it gets over to 2. Of course, we're not graphing this up to 100, but that is going up very fast, right? But a smaller number like 2, well, 2 squared is just 4. So by the time we get to 2, we'll only be up at 4, like the point we see there. Okay, so bigger the base, steeper the line. Got it. Also notice this point, the y-intercept. Did it change? No, all three lines share the same y-intercept, but why are they all the same? Why? Think about it. And it's because anything to the power of 0 is 1, right? And y-intercepts have an x value of 0, right? All y-intercepts have an x value of 0. So here, 10 to the 0, well, that's 1. 3 to the 0, that's 1. Same thing here. That's why they all share the same point. When x is 0, y is 1. Right there. Okay, so we're learning some things about exponential graphs. And there are a lot of ways we can transform the graphs of exponential functions, and sometimes more than one happen in a single function at the same time. And you might think, oh boy, this is going to get confusing. Don't worry, focus on taking good notes, and we're going to use the Desmos calculator. Okay, this is the graphing calculator, different than the scientific calculator. Okay, all right. So we're going to experiment with exponential functions and understand this better. let's talk about exponential functions with negative exponents. Okay, we're going to go ahead and type these into the Desmos graphing tool. I'm going to do that now on my other screen. You should be doing this too. Y equals 2 to the power of x. Okay, and y equals 2 to the power of negative x. Now let me see if I have it on the next screen, but first, think about what changed when you graph the second equation. And if you're not familiar with this graphing calculator, clicking here or here can remove that graph. So if I only want to see this graph, then I would click on there to make it basically just look like a blue circle. So let me show you really quick. I'm going to share my uh, screen with you here. So here you see the two functions or equations typed in. If I only want to see the red line, there it is. If I don't want to see any lines, click them both off. But here's the red line, and then here is the blue line, the second equation. So look at those and think about what changed when I graph the blue line. Something very obvious changed, right? One looks like the mirror of the other. They're symmetrical. Where? Where would the mirror be looking at this? Well, it'd be right on the y-axis, wouldn't it? And this is, think of this as a mirror, and this is a reflection of the other. So now keep your first equation and change your second one to this. Instead of the exponent being negative, we're going to make the base negative. Whoa, look at that. It looks again like a reflection, like a mirror, but where's the mirror now? It moved, right? It is laying on that x-axis because this looks like exactly the opposite of this in relation to the x-axis. Okay, we're experimenting, we're figuring this out as we go. Now, let's go back to the lesson slides here. And the question now is, can you graph the general look of this exponential function correctly? And the clue here is there are multiple transformations. Okay, so go ahead and give it a try. You can use your Desmos graphing calculator if you'd like. Okay. Now, what happened? Let's see what happened. My recommendation to you is to first graph the original function without any negatives. So x-intercept of 1, because again, anything to the 0 power is 1. And there is another point at 2, 4, right? Because right now we're just pretending that these are both positive, right? If I put 2 squared, that would be 4. So something kind of like this. Notice it starts off really close, almost looks like it's on the x-axis, and then it kind of goes up like that. But things are about to change, right? If we go back to Desmos, we see how things have changed here, right? And we're going to walk through it one step at a time. So we had this red line. Just like before, if you make the base negative, it reflects over the x-axis. And then if you make the exponent negative, it reflects over the y-axis. So two different things are happening. And when you're reflecting over the x and the y-axis, you actually say you're reflecting over the origin. Over the origin right here, right? Doesn't this look like the mirror is here, and it actually is. Let's be more specific and show you exactly where the mirror is. When you have a reflection over the origin, the mirror goes through the origin and it's at 1, 1, 1, 2. There's just a nice simple slope of 1. So this, and I'm not going to graph it as a solid line because this is just showing us where that mirror is. Okay. So the other line is something like this, right? It's looking like that mirror effect. Let's get the line going like this. And it would be -2, -4, something like that. Okay. And this line, this dashed line, do you know what the equation of that line is? Well, think of slope-intercept form, right? Y equals, is there a slope? Yeah, it's 1 over 1 or just 1 or 1x. Is there a y-intercept? Well, it's just 0, right? So the line you're going to see is y equals x. That's the line, the dashed line here. Okay? Y equals x. Now, that's if the base and the exponent are both negative. Okay? Now, let's talk domain and range. Remember domain and range? I'm sure domain, we've looked at that a lot this year. Range, not so much, but we will today. Domain is all the possible x values. Range is then all the possible y values. And interestingly enough, all of these lines have the same domain and range. Do you know what they are? Hmm. Write them down. Take your best shot. Write them down. Let's see how you did. Domain here is all the possible x values. Well, these arrows, all of them are going to go left forever, right? So all the way from -infinity, and how far right will these lines go? Well, they're going mostly up, but they are all moving slightly to the right, aren't they? So if we're going all the way from -infinity to +infinity, you can write your domain like that, or you can write it like this, which means all real numbers. From -infinity all the way to +infinity. Now range, how high up and how far down? Well, you want to start at the bottom first. So how far down does this get? Now you might be looking at this and thinking they all just lay right on that x-axis, right? And if a solution's included, you would have the brackets, right? So you might be thinking 0, and then of course all these lines are going up forever. But there's something very, very interesting happening right here. And let's go back to Desmos to actually see what's happening. Okay, so here we are. We're going to go ahead and put in all of those same equations. So we have 10 to the x, 3 to the x, and you can just click here to make a third line. There we go. And y is 2 to the x. Okay. So this is what we have, what we just looked at in our lesson. And look at these. You're thinking these are on the x-axis, but let's actually zoom in to be 1000% sure. We're going down to the x-axis. Okay, okay. Red's basically touching, right? It's touching? It looks like it's touching. I don't know. Let's zoom in more. Oh, it's actually not touching? Okay, it's getting closer. Sorry, it's getting closer and closer. Is this ever gonna touch? What's going on? That blue line I see again. Okay, now it's touching, right? Zoom in again. It does not. So this is an extremely interesting concept, these lines actually never touch the x-axis. As close as they get. That's an interesting concept, right? It always gets closer, but it never touches. At some point, it's got to level out, right? So let's go back to our lesson and see what's actually going on here. Um, is zero included? No, zero is not actually included, but it goes right up to it. So anything above zero, all the way up to positive infinity. And do you know what that line is called? A line that another line never touches? In this example, it's our x-axis. So that is called an asymptote. And specifically, this is a horizontal line, so this is called a horizontal asymptote. There are also vertical asymptotes, which we'll get into. Interesting stuff, right? These are very specific types of graphs that behave a specific type of way. Now, we talked about what so far? Let's just go back. We talked about reflections, basically, right? Reflecting over the x-axis, the y-axis, and the origin. And then we looked at something interesting about the domain and range and learned a little bit about asymptotes. And now we're talking about another type of transformation, which is moving the function up or down. This is called, if you're moving it up and down, it's called a vertical shift. Okay? And be very careful here because look at these lines. What kind of line is this, and this? Well, you might be thinking, I know, you just told us it's an asymptote, right? Yes, it is horizontal, yes, but how are our graphed lines moving? If you look at that blue, orange, and red line, they're moving up and down, right? We're not stretching them right now. So when you're thinking vertical shifts, imagine it is like a metal rod and you're holding it and you're just moving it up or moving it down. Okay? So this is where the terminology gets a little tricky. Stick with me. Vertical shifts happen when horizontal asymptotes move, right? Let's take a look at it. Okay? If you were adding something at the end of your equation, your exponential equation, that means there's a vertical shift up. This is super important, okay? And of course, you can guess it. Oh, where did my lesson go? There it is. If that number is less than zero, so we're subtracting, that's when you move down. And we see that over here. H of x equals 2x minus 3. Well, remember, the parent function had the horizontal asymptote at the x-axis, right? So if we're subtracting 3, every point is going to move down 3. We're moving down 3 every single place, okay? All right, and the same train of thought with the other option. If you're adding, here, g of x is 2x plus 3. Well, every single point is going to move up 3. And my advice to you when moving lines, aka applying vertical shifts, start with the horizontal asymptote first, and then graph the rest from there. It will just make your lives easier. Okay. So the horizontal asymptote, well, that's at the line where y equals whatever value you added or subtracted, right? If you added 3, then y is positive 3. If you subtracted 3, y is negative 3. That is the actual equation of your horizontal asymptote line. And of course, if it's on the x-axis, y is equal to 0. All we're doing is moving everything up and down. We're not stretching this line. We're not flipping it. So adding and subtracting, that's the effect it has. Now, you guessed it, moving left and right is also an option. When does it happen? Let's see. When you add a number to the exponent up here, that's going to move the whole function to the left. Okay? So what would happen if you subtract? Then you're moving it in the opposite direction to the right. And this is very counterintuitive. Remember dishonest H? Well, he's back. H is dishonest. It's the opposite of what you see. If you see +3, you're thinking, oh, positive. I'm going to move in the positive direction on the x-axis, which is to the right. It's actually not. We moved every point to the left 3 units, right? Did the horizontal asymptote move? No, it did not. Okay. And on the contrary, you guessed it, if you are subtracting like you are here, you're going to move every point to the right 3. Huh. Dishonest H. Always the opposite. What a sneaky guy. Always the opposite of what you think. What is the y-intercept? And does it change now? Let's see. Here it's 0, 8. Here it's 0, 1. Here it's like 0.2. Yeah. Now the y-intercept is moving. Why? Because we're moving the lines left and right. And it makes sense, right? If you're having, let's say you plugged in 0, 0 plus 3 is 3. Oh, so that's why we no longer have 2 to the 0 power. We no longer have 2 to the 0 power. This would be 0 minus 3. That'd be 2 to the negative 3, right? Okay. All right. Let's move forward. We've talked about reflections. We talked about moving left and right, up and down. But can we stretch and compress? So remember, stretching and press is like a rubber band. Now the line is like a rubber band, and yes, we absolutely can. Okay, here we go. If the absolute value of A is greater than 1, there's a vertical stretch. Where is A? That's in the front. So here we go. The absolute value of 3, remember, absolute value is the distance from 0. Distance cannot be negative. Okay, so absolute value of 3 is 3. Is that greater than 1? Yeah. So there is a vertical stretch, and we see that, right? The orange line was the just 2 to the x, but now when we're multiplying it times 3, like we see here, everything is getting stretched. So all these points are moving up, but pay close attention. Did the horizontal asymptote move? No. We are keeping it where it's at, and we're stretching these lines vertically, right? By a factor of 3. Every y value is going to be multiplied times 3. Okay, let's look at when it is compressed. Vertical compressions happen when the absolute value of A is between 0 and 1. So right here, 1/3, well, the absolute value of that, again, that's a distance. Let me clean that up. Is 1/3. So yeah, that's between 0 and 1. That's why there's now a vertical compression. You're flattening it out, right? You're pushing it back down closer to that horizontal asymptote at the x-axis, right? So all the y values are getting chopped in thirds, right? And if you're wondering why absolute value, what's going on with this? It's just because what if there's a negative? Remember the negative sign in front? Like let's say this equation was instead g of x equals negative 3 times 2 to the x. Remember the negative was its own transformation. Do you remember what it was? Let's go back for a second. Sorry, things are moving around a bit. Um, right here is when we did that, right? First we did the exponent, then we did the base. Do you remember what happened when the base was negative? If you don't, go to your Desmos calculator right now. Experiment with it. And if you zoomed in a million times like I did, you can refresh the page. But remember that negative reflects over the x-axis. So use that Desmos graphing calculator as much as you can. All right. So vertical stretches, vertical compressions. Is there anything else? Well, let's see what would happen here. We're talking about vertical stretching compression, so we're really just testing our understanding. What would happen to the graph if we added 2? So this is the graph we see right now, right? That's the graph we see here. But what happens if we add 2? Check your notes. And I don't have it right there, so let's go back. What happens when you add to the end of the base? That is a vertical shift up. Okay, so here we're adding to the base. So that's a vertical shift up, and you start with what again? You start with the horizontal asymptote, which is the equation y equals whatever that value is 2. So here's our new horizontal asymptote. We'll put HA for short, and it's the equation y equals 2. That's the actual equation of that line. Now the rest can just be graphed as it was. So we have that blue line. I'm just going to roughly graph it as it was. Okay, so this has several different transformations going on. So it's important you have all of the transformations in your notes because you got to know what's happening when and why. Okay, what about this one? Horizontal compressions. Okay, we haven't talked about this yet. Horizontal compression. So we're talking about left and right. We're talking about either squeezing it together like this or pulling it apart like that. And when does it happen? Well, of course, there's a rule for that as well. When the absolute value of K is greater than 1, horizontal compression. So where's K? K is touching X. So if you see a number being multiplied with X that has an absolute value greater than 1, there's a horizontal compression. So let's take a look. There's a number here next to X. So that's K. That's what we're focused on. The absolute value of 3 is 3. Is that greater than 1? Absolutely. So there's a horizontal compression. And you can see that, right? You can see that. The blue line, sorry, the red line was the parent function. Okay? And notice what's happening. These lines are it's getting squished in, right? And it's getting squished in. They're getting closer and closer to that y-axis. Okay? And what about the other situation? Well, it again has to do with those values between 0 and 1. So if that value being multiplied with x is between 0 and 1, then you have a horizontal stretch. So notice what's happening. Parent function, we started here, red line. And notice what happens. We're stretching, so every point's getting stretched out, this time further and further away from the y-axis. Interesting. And it's actually by a factor of 3. Notice, for example, let's go with a point that's easy to see. 1, 2, this point here. While it moved to the right, you can see 3 is there, right there. So this point was at 1, 2. Now it's at 3, 2 by a factor of 3. And actually over here is where it gets divided. So that might be counterintuitive as well. You think 3 means multiply by 3. It actually is going to mean divide in this case. Okay. So horizontal stretches and compressions. I know there's a lot of transformations. We're covering them all today, but you can rewatch this as many times as you need to and ask me questions in class or via email. Okay. Almost done. Finally, sorry, the absolute value of b is between 0 and 1, we have exponential decay, and the same earlier rules apply. So we're talking about the value in here and the value there. Okay, so let's take a look. When this value is between 0 and 1, like this is, there is exponential decay. We talked about this before, right? This isn't our first time looking at this. If this value is greater than 1, there's exponential growth. And the y-intercept is what? Did it change from one to the other? No, it did not, because 1/2 to the 0 is 1. Anything to the 0 is 1, and 2 to the 0 is 1. So they share that y-intercept. All right, so that is it for today. If you need more practice, watch this again, like I said, or ask me for help. You can also always study the resources in the OLS by going to functions, this lesson, graph exponential functions, and then there's learn, practice, all sorts of good resources in there. All right, see you guys later.